Okay, so good morning everyone. So the topic of today's lecture is on the boundary conditions such that the boundary conditions are not fixed but variable. So in this lecture and in the next one I am going to talk about specific cases when we do not have fixed boundary condition on the integral endpoints. So the part 1 of our lecture is on variable boundary points. Okay. So, in this lecture I am going to look at a very special case of variable boundary points, followed by the more general case in the next lecture. So, let us revisit our original functional optimization problem. Note that for the fixed endpoint problem, we had the following functional that we need to extremize. We needed to extremize the functional g of y such that g of y is integral of f x y y prime dx, and x is from x 0 to x 1, and this was subject to y of x naught is y naught and y of x 1 is y 1, subject to these two following boundary condition. So, the variable endpoint problem we are going to look at in this lecture, we are going to look at the class of variable endpoint problems where we only vary the y component, the x component is still fixed. Okay. So, the problem that I have, well, the variable endpoint problem. Okay. A very common example in this category which we are going to discuss in detail is the problem of bending beams, right. Say for example, if we have a beam or a steel rod which is, let us say, clamped onto the wall at one end, and it is possible to bend the beam under action of a load. So, in that case, one of the end being clamped, the boundary condition still applicable at this clamped end is the fixed point boundary condition. On the other end, since the other end is varying, we will have to figure out a new set of boundary conditions for this variable endpoints. So, a beam clamped on one end, and in that case, as the diagram shows, we can very well assume that. So, this is x equal to 0 and this is x equal to L. So, y at 0 is equal to the slope at 0 is equal to 0. So, we still use the fixed point boundary condition at the fixed end. Okay. However, at the variable end, there is no such boundary condition. So, there is no boundary condition because there is no boundary at all. Well, the question is, then we do need extra conditions to completely describe our extremal solution. So, where are we going to get those extra condition? The answer lies in the setup of the extremal itself. We know that the extra conditions that are needed to fully solve and find the extremal of the solution of the functional is coming from the fact that the functional is stationary, right. So, we want to find the conditions at the variable endpoint such that the variation in the functional is at most of order epsilon square, or in other words, the variation in the functional is negligibly small. So, the extra condition comes from the fact that the functional that we are trying to optimize is stationary, okay, or has extremal solution is stationary, and this condition, the imposition of this particular statement will lead us to the development of new conditions known as the so called natural boundary condition. We will see that the natural boundary conditions, they reduce to the fixed point boundary condition if we fix the free end. Okay, so the natural boundary condition turns out to be a more general class of boundary conditions, of which the fixed point boundary condition is a subset. Okay. Okay. So, let us now build the background on finding these set of natural boundary conditions. So, let us say we are given a domain. Let us say we are given a domain from with x coordinate from x0 to x1. So, these are fixed. So, I allow these x coordinates to be fixed, but I allow the y coordinates to vary. So, let us say we have a function y of x, and now if we want to perturb the function y hat. So, earlier y hat was such that the endpoints used to match, right. So, now not anymore. So, if we have y hat, let us say this is my y hat, and now the endpoints are, so in this case the original y had endpoints at x naught y naught, and the new perturbed quantity or the perturbed function has the endpoints x naught, let us say y naught hat, and from x1 y1 to x1 y1 hat. Okay. So, if we were to describe this perturbation as the original function plus epsilon eta, then no longer does the perturbation eta going to satisfy the 0 endpoint condition, because the endpoints are not going to match for the perturbed and the original function. Okay. So, suppose let us start building this setup. So, let me call this case study as A, because we have more case studies along the similar lines. So, suppose I have the functional j, and the j has an extremum. So, I need to number some of my equations here. So, I call this as 1 in the previous slide, and I call these boundary conditions as 1 prime, right. And let us proceed further. So, suppose j has an extremum, at y, j has an extremum at y with no boundary condition, and your y is a second order differentiable function from x naught to x1. Okay. And let us consider the perturbation. Consider the perturbation in the function y, which is y hat is equal to y plus epsilon eta, right. Now, again eta, we still require eta to be continuously differentiable up to second order. However, this time eta will not satisfy the 0 boundary condition, because the endpoints do not match. Okay. So, the clear difference being, since no fixed point boundary conditions imposed, it implies that eta does not vanish at the boundary, at the fixed point boundary condition problems, eta used to vanish, the perturbation function. Okay. So, let us now write down the variation of this functional j. So, the variation of the functional j, we use again some of the starting steps are similar to the standard fixed boundary problems. We find out what is the perturbation of j, what is the functional j in terms of the perturbed value, and express the functional j in as a function of perturbed value in terms of the functional j as a function of the original function y, and then we take the difference, and then we arrive at a point which is as follows. So, the linear order terms are as follows. We arrived at a point earlier that this is the following. Okay. Now, from here, so this is my order epsilon term. From here what I get is, we can do integration by parts, and we see that this is also equal to eta del f del y prime from x0 to x1 plus integral from x0 to x1 of eta times del f del y minus d dx of del partial f partial y prime, okay, dx. So, this is the point where we use to impose our vanishing condition on eta for this first quantity, right, and then use to extract the Euler-Lagrange equation. But now, since eta does not vanish at the boundary, this question is what next can be done. Well, note that eta belongs to the class of perturbation functions, right, but the only new thing now is that eta does not vanish on the boundary. However, if we consider, so if we consider a new if we consider the perturbation from a subset H naught, which is a subset of H, where my subset H naught is the set of perturbation functions where eta vanishes at the boundary, So, certainly H naught, where which is the set of all perturbation functions where eta vanishes at the boundary, is a subset of the general class of perturbation functions. So, if we consider this eta, then this particular eta, which is also in H, should also satisfy, let me call this as 2 here, okay, because my 1 is this quantity here. So, I call this quantity as 1. Okay. So, certainly for this eta, let me call this as eta naught, right, to distinguish from this eta in the general class of perturbation function. So, for eta naught, certainly 2 is satisfied, right, and eta naught is quite arbitrary. So, which means for an arbitrary eta naught, this integral will be 0. So, this is this quantity is my 2. Okay. So, for an arbitrary eta naught, it turns out that well, so eta naught vanishes on the boundary. It turns out that 2 must be identically equal to 0, which means that again using lemma 2 in our lecture 2, we can come again to the same set of conclusion that partial f partial y minus d dx of partial f partial y prime is equal to 0, where this is nothing but our original Euler-Lagrange equations which are recovered, right. Okay. So, then let us consider the most general eta. For the most general perturbation eta in H, note that given 2 is equal to 0, 1 is going to vanish only when the coefficient of eta vanishes, right. So, for a very general eta, we must have that 1 is identically 0 if and only if I have that the coefficient of eta vanishes. Okay. The coefficient of eta vanishes, and well, let me term this Euler-Lagrange equation as my A, and note that, well, call this as small a, and this is my new class of conditions which I call as B are my, this new class of conditions are my natural boundary conditions. Okay. So which means we will replace fixed point conditions at the point x1 y1 with B. Okay. Okay. With B if no fixed point conditions are given. Fixed point conditions given. Okay. So, let us quickly look at an example to see what this new condition, how this new condition works. So, a simple example is finding the extremal of the arc length. Okay. So, extremize the functional j of y, which is integral 0 to 1 square root of 1 plus y prime square dx, subject to, well, so integral from 0 to 1, so we need to extremize. Okay. So, now we are just given that, so we are not given any boundary condition here, we are only given, that x naught is 0 and x 1 is 1, right. We are not given what is the value of y at x naught and y at x 1. So, no fixed point boundary conditions given. So, now it is assumed that the boundary conditions in general is, for the general class of such problems is for the variable case, or we are going to use natural boundary condition. So, let us so even before we go ahead, we know that for the fixed point problem the solution to this arc length problem was a straight line, right. So which means y is extremal. So, y is extremal if y satisfies our condition A, y satisfies A, which is this Euler-Lagrange equation, and from here we can directly get that the solution is a straight line, y is equal to mx plus b, right. And then since we are not given any extra boundary condition, we can impose condition B. So, from B I get that del f del y prime at x naught to x 1, So, let us differentiate our integrand. So, this is my f, differentiate with respect to y prime, I get that this is equal to y prime divided by square root of 1 plus y prime square. So, this, now note that we have already find the extremal, right. All we need to find is the value of m and b, and we do that by plugging our solution into this natural boundary condition. We get that this is also equal to m divided by square root 1 plus m square. We set it, so at x 0 to x 1 this is equal to 0, right, and that is only possible when m is identically equal to 0, right. So, the conclusion here is that the extremal that we get are constant, y is equal to constant, or the extremal that we get are lines which are parallel to the x axis. So, that should be quite intuitive, because the functional j will attain the minimum if, well, the functional j will attain the minimum. By the way, it can only attain the minimum because this is in the quantity inside the square root is a non-negative value. So, the j attains its minimum only when y prime is 0, and that is only possible when y is a constant. So, which means that my solution is y is a constant where b is arbitrary. So, it is a arbitrarily set constant value. Okay, so that this example was quite simple. Let us now look at another example of the catenary that we have done so many times. Okay. So, catenary revisited. Okay. So, I extremize j of y, which is integral from 0 to 1 y times square root 1 plus y prime square dx, subject to the boundary condition y of 0 is equal to h. We subject to the boundary condition that. So, we are given one boundary condition, however, we do not know what is y at 1. So, we are not given the other boundary condition, which means it is a case of variable endpoint problem. So, again when we extremize, we already know we are going to, the extremal y is a cos hyperbolic function. We have already solved this example so many times. So, let me write down the extremal solution. The extremal y is such that y is the cos hyperbolic function kappa 1 cos hyperbolic x by kappa 1 plus kappa 2, right. And also we are given one boundary condition, given that y of 0 is equal to h, or I get that h is equal to kappa 1 cos hyperbolic kappa 2, right. Okay. And then to find the other constant out of kappa 1 and kappa 2, we impose the natural boundary condition at x equal to 1. So, we impose the natural boundary condition at x equal to 1 to see that I get del f del y prime at x equal to 1 is 0, right. Okay. So, when we differentiate our y, we plug in, well, not this one, so this is my f. When we differentiate with respect to y1, I get that y prime divided by square root 1 plus y prime square is equal to 0 at x equal to 1. We already have the result for y, we just plug it into this condition and we see that the condition we get is the following. So, y of 1 times y prime 1 divided by 1 plus y prime 1 square under the root, and this is equal to 0, right. Okay. So, certainly note that we are dealing with cos hyperbolic functions. We do not expect the slope at any point for the cos hyperbolic function to go to 0 except at the minimum point, right. The cos hyperbolic function will only have one minima. Certainly that will not be equal to 1. Not that situation. Well, what so from here what we have is either what we can conclude from this condition, let me call this a star, is that either y of 1 is 0 or y prime 1 is 0, right. Now, if y of 1 is 0, what is going to happen? We have a catenary where at 0 the curve is having a height h, and at 1 the curve is lying on the ground, right. So, we have a very abnormal catenary where part of the catenary is touching the ground. This is not a very plausible situation. So, the only other plausible situation is where the slope vanishes, right. So, if the slope vanishes, we evaluate the slope at 1, and from here I get a relation between kappa 1 and kappa 2. I get that kappa 2 is minus 1 by kappa 1, and further I get that my solution y now in terms of the one parameter family is x minus 1 by kappa 1. That can easily be found using my boundary condition. since I have that y of 0 is h. So, I plug in 0, I get that this is kappa 1 cos hyperbolic 1 by kappa 1. So, which means if I take my 1 by kappa 1 is equal to xi, then I get the equation that h xi is equal to cos hyperbolic xi. So, this is the same standard equation that we get in order to solve for the roots of the catenary. It is a transcendental equation, and in general for h large enough, it is going to give us two solutions. So, I am going to stop the discussion on this example, because the solution, the most general solution, has already been discussed in our previous lecture, but this example highlighted the way how we can use the natural boundary conditions, right. So, then we are going to look at another case where we can, and how does the absence of fixed point boundary condition changes that case. The case that we are interested to look at are the case where the functional involves higher derivatives, right. So, we have a functional that involves higher derivatives, the functional that involves higher derivatives, right. So, j of y is integral from x 0 to x 1 f of x comma y prime comma y double prime is equal to times dx, right. Let us say up to second derivative. So, then again we set up the variation, set it equal to 0 and do integration by parts, and we are going to come to a stage where we have the following expression. So, the variation of j comes to the stage that we are given the following equation, del the second derivative with respect to x of partial f partial y double prime minus partial f partial y prime plus partial f partial y, right. So, this is the standard differential form times eta dx, plus we also have the following set of quantities which now do not vanish, plus eta prime df, well, partial f partial y double prime at x 0 to x 1 minus eta times the ordinary derivative with respect to x of partial f partial y double prime minus partial f partial y prime. This is from x 0 to x 1, right. So, we see that again using our specific class of perturbations, and from lemma 2 of lecture 2, we can get that from the first part, let me call this as 1 prime and let me call this set of expression as 2 prime. So, from 1 prime I get my standard Euler-Poisson equation. So, the conditions for extremal are going to be along the similar lines. We can conclude that the conditions will be such that the extremal will be such that it satisfies this bracketed quantity inside the integral in 1 prime, which is the Euler-Poisson, and the other two quantities which are my 4 natural boundary conditions. Okay. So, what I get is the following. The condition for extremal is the second derivative of partial f partial y double prime minus the first derivative partial f partial y prime plus partial f partial y is equal to 0, which is my Euler-Poisson equation, and along with the fact that eta prime of del f del y double prime, right, this So eta prime does not vanish in general. So we can impose for an arbitrary eta, we can impose that this is 0, and the second set of boundary condition that we have is d dx of partial f partial y double prime minus partial f partial y prime at from x1 x0 to x1 is 0. So these two sets of or 4 conditions are my 4 natural boundary conditions, replacing the fixed point conditions. Okay. Okay. Now certainly if there are fixed points in the problem, then for those fixed points the fixed point condition are going to replace the natural boundary condition without any confusion. So let us look at our next example